Swayam Prabha. Digital India. Educated India.
Sweating, summer, Chennai, solar energy, May month, dehydration. The very fact that I'm searching means I'm yet to get that answer. Ice cream and cold water, humidity, desert. Okay. A typical inventor would ask, what temperature is it? Surprising? That's the question they will ask, because they want to relate to what that parameter that connects to saying hot, too hot. Now it's easy for you. Too much noise in the school. What's the decibel level? Now you see, you're now getting it. Bright sunshine. Lumens. Am I heavy? Hey, say I'm light here. Doctor's prescription. Milligrams. Dose. Finishes the homework fast. Yeah. Yeah. How many minutes per problem? Yeah. Quality of the answer. Water level has gone down in reservoirs. This is important because Chennai, depth reduction, volume, liters, huh? Cubic meters or cubic feet, cusecs, right? If it is a flow, it is cusecs. Heavy traffic, number of vehicles, not enough. Density rate of the vehicles. Okay, last one is large class, small class. It's very dicey, you know. What do you say? Is this a large class? I may say it is a large class. You may say it is a small class. Raise your hand and talk. Yeah. What is it that determines small or large class, right? Whether the teacher perceives that as a large class or the student perceives as a large class, etc., etc. Okay, let's see one more habit. Your mom asks you to go and buy potato in the market. Oh, she never does, and is not an answer I want.
Price per kg.
Huh? Price per kg. How many kgs? How much do you want me to buy? Right? So you can't say, oh, okay, you want me to buy potato? I'll go. What's the point here? You need to ask half kg, 1 kg, right? Okay. Shirt or pant, does it fit me? Does it fit me?
Dimension for the shirt, like
shoulder dimension, very good. Bright bulb, wattage. Quantity in a food packet. How many of you look at quantity in a food packet? Really? Wow, wonderful. Continue that habit. Milk sachet.
Which kind of milk it is?
Expiry date, very good. Is it pure milk? No, I'm asking, is it a pure milk? How do you do that? What is it called? Huh? No, what is that meter called? Lactometer. How far is the library from the gate? It is 1300 and no, 10,300 centimeters. Appropriate units you have to use, right? What unit would you use? Perhaps kilometer, right? Train ticket?
Where is which train?
Yeah, distance, price, and so on. Okay, one more is there. Okay, recipe instructions.
Time.
Right? So, good. The reason I am showing these two slides is for you to get into that kind of a habit. If you want to be an inventor, always that if is there. Height of a room generally is 10 meters, 10 feet. What would be this height? Yeah, around 12 feet. Yeah, 12 to 13 feet. Yeah, good. What am I doing now? Estimating, guessing, right? Based on what? Usually our height or our span of arm, right? Remember, in the olden days, that's what people did. Why do you think we have feet, we have span, etc., etc.? All those came out of our own limbs. A typical length and breadth of a hotel room. I'm sorry, hostel room. Because you may go to a hostel pretty soon, no? Huh? What would be the length roughly?
6, 7 meters.
Usually it is 8 feet length by around 7 feet. That's all you have. Okay. Okay. This is a sort of comfortable room that you would have if you come to IIT. Distance between Chennai and Bangalore. 650 kilometers he's saying, and he's saying 200 kilometers. By road it is about 350 kilometers. Straight, if you look at, it's around 280 kilometers. Very fast ball delivered by a fast bowler could be.
148.
But why would you be interested in that? Okay. Okay. Height of an average Indian. Yeah. Okay. This is a little difficult. Long jump. 5 meters. Okay. High jump record. 2.2 meters. I think recently it was broken, but by a very small margin. Fastest speed of man. 35. It has been broken to a certain extent now. Okay, so I'll skip this for want of time. We'll do an activity. Yeah? Now, what were we talking about so far? If I have to put one, measurements, right? So let's do some measurement. What I have is just a strip of paper, but I know the length of this. I'll tell you the length of this. Okay. All right. So take one strip out. One strip out. How do you make it a ruler? Now, this length, I'm sorry, that's a mistake. This length is 16 inches, not 8 inches, 16 inches. Okay, I want to make it a ruler. What will you do? Fold it. So many of you said, so no chocolate. Yeah, fold it in half. Okay, fold it in half. Then again in half. Okay, do it. So now you're making a ruler. Once you fold it at the crease, you just mark it using your pen. Okay, so you know, and it will always be in multiples of 12. No, more than that. You want to have a bet? I'm good with length. It has to be about 14 to 15. 15, no? Wow. Yeah. Let's take it as 16, okay? 16 is the length that I am giving you. The length of the strip is 16 inches. That's what I have given you as a information. I want you to make a ruler out of it. Doesn't matter, just make a ruler out of it. What would you do? You would fold and then mark it, and the marking would be such that it will be only multiples of, the divisions would be multiples of, it would always be in terms of 2, right? You fold means you make it into 2 parts. So each time you fold, it will be 2, 2, 2, 2, 2 and so on, right? So you can make into 16 of them. Yeah, do that and mark it. Because there is a beautiful story behind it, that's why. Quickly, yeah. Huh? 16. No, no, make it 16 because how can you make it 15? How can it be here? See, I fold it 1, 2 and so on. No, 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 no. You folded it and made into 16, correct? Mark. And make sure that it's a ruler. So you just do like this, it will become a ruler now. Done? Done? Okay. Mark it, mark it, mark it. Ashwin, done? All right. Wow, very good. Okay. So now take some object. Let's say your mobile phone. Mobile phone, I want to measure the diagonal length of my mobile phone as accurately as possible. As accurately as possible. From the edge that you know to the other diagonal edge. Accurately I want. Roughly 7, don't say roughly, you have a ruler. 7.5 what? 7.5 inches. Okay. 7.8 inches because the entire thing is 16 inches. I have given you a strip which is 16 inches long. 7.7, no, you have to be accurate. 7.7, okay. 8, wow, you have a huge one. 8 inches. Yeah, Devi. 7.2, small one. 7.6, okay, 7.6. 7.75, 7.75, 75, huh? 3/4, 3/4, that is 3/4, no? Okay, 7.5. Okay, question cannot be written, yeah, go ahead. Exactly, that's the question I have. So between 7 and 8 you can say approximately. So if you want to say, oh, okay, it is nearer to the middle, 7.5. If it is between middle and this, 7.25. That's what is the guess that you made, correct? Now I want to make it more accurate. Like Manasa wanted, I want it to be more accurate. What can I do? Do it, do it. And then give me the figure. Give me the figure. You're getting exactly 7.5. Okay. Then measure somebody else's. Huh? No, no. I want more accurate. I want more accurate. I didn't ask you to fold. You said I would fold. Yeah? You folded into some more, is it? I want more accurate, more accurate. Yes, 7.7. No, I can't believe it. Where you folded and found out, huh? You folded it and found out. No. Why can't it be one more digit after 7.7? I want more accuracy than 7.75 that he said. Oh, no, I didn't ask you to fold. I didn't ask you to fold. You folded it. Huh? Exactly. No, yeah, 7.747. No, it is 7.47. 747. You know 747, no? No. Now, just freeze statue. What is HCF? See, in the movies, director switches the scene to something else, no? So I'm going to switch the scene to something else. Highest common factor. So if I'm given two, let's say N1 and N2, two numbers, you can find out HCF, right? Two integers, you can find out. What is co-prime? Whose HCF is 1, right? Give me some example. 14 and 15. Why can't it be 15? Why can't it be 15 and 16? Why can't it be 16 and 17? Why can't it be 17?
That's one example I gave.
Yeah, one example. Any two consecutive numbers. All right. So Adi and Naomi. Adi and Naomi start from that end of. So listen to me carefully. Start from that end of the room and ends up in that end of the room exactly. But one has taken 10 steps, whereas the other has taken, because he is very tall, he has taken 9 steps. Where will they meet in between? Where will their legs meet exactly? Within this room.
Starting and ending.
Wonderful. Wonderful. Which means now I am talking about co-prime, correct? Yeah? This is a clue for you. This is a clue for you. Chocolate question. I've given you a clue. What did I want? Accurate. And then I gave you a clue. Wonderful. Here. Ouch. Vernier said, well, take one more strip. So take one more strip. Do as I say. All right? Do as I say. You folded, no? Right? You take that strip, tear off one of those divisions. Can you? You did the folding, no? Tear off one of the divisions. Now we have 15 of them, correct? Yeah? Now the first one. Done? Done? Huh? You take the second one. Make sure that the length is exactly the same as the first strip that was cut. Did you understand? You will tear off one division from the first strip. You take the second strip and make sure the length of the second strip is exactly the same as the first strip after the first division has been cut. Quickly. You understood, no? I have this division. Now I have cut it. I have like this, so I put them together now. Oh, okay, this is the excess. I'm going to cut this excess. The second strip is now ready. First strip is already there with all the folds and lines. Now I will take this and do the same thing. Fold it, fold it, fold it, fold it. Did you get what I meant? One had 16 of them, 16 inches folded, correct? Now you are doing 15 inches folded. So what did you do? You took two co-prime numbers and divided the same way. Now if I ask you, if I put one along the other, where will they meet? Where will those markings meet? Starting and ending only. Beautiful, no? And what he did was, if I slide one strip over the other, it is possible for me to go into a count which is the difference of the two divisions. Right? Beautiful. Just the co-prime, Vernier thought a little differently. Instead of just folding further and further, he said, why don't we use co-prime numbers and arrive at this solution for more accurate measurement. Beautiful, no? When did he do this? When did he do this? You will not believe this. Oh, okay, we have done this. 16th century. But wonderfully, he came up with vernier calipers, but that was not the end of the story. I wanted more accurate, which means I need to have a long strip, correct? How long can I go? Screw gauge. What's the idea of screw gauge? I move forward in one direction and rotation in the other direction. Another invention. Yeah? Okay, screw gauge was born. And then traveling microscope, very similar principle. That's not the end of the story. The other revolution occurred when someone realized this. Okay, anyway, we'll come to that. Just have a look at this. This is 100 divisions. 100 divisions on lengths which were 199. All right. So look at what has happened here. If you notice carefully, here it seems to be more dense and it is sparse at these places. And if I move one over the other, can you see that moving? Oops, how do I do this? It doesn't work there. Can you see it moving? Can you see it moving? Beautiful, no? This I used just PowerPoint and did this. You can see it moving beautifully. The left way it is moving. Can you see that? Okay. So, okay, sir. So, what if it is moving, right? Here also you can see it moving. You can see it moving very nicely. You can see that there is a band that is moving. Yeah. Next invention. These are the markings on the ruler. I'm going to now magnify it. Yeah. And it looks like this. It looks like this. What do you notice? Darker at the center, lighter at the edges. And if I draw the intensity as the y-axis with respect to x-axis with maximum intensity, etc. Let's say maximum intensity of blackness. How will it look like? These are the critical points and it will be like this. What is this? Huh? What is this? Sinusoidal, okay. One more word you can use. Huh? Huh? Periodic? Wave, wave. Oh my God, wave. What is a wave? What is a wave? What is a wave? Sound? Sound could be a wave. Sound could be a wave. So if I take one sound, think of how the inventor is now thinking. If I take one sound of a particular frequency, change it a little bit, superpose, I get beats. Right? Wonderful, I can use that idea. Waves. Sound waves, okay. Light waves. Electromagnetic waves. Right? So now I'm suddenly jumping from a ruler with markings now to waves. And if I do the same thing that Vernier did, two co-prime waves coming together, what would happen? It will form a pattern like this called the interference pattern. And this interference pattern can now be used in order to measure more accurately. How accurately? Well, sir, it depends on the frequency of that particular wave, right? How much can you go as far as frequency of a wave is concerned? It is not limited by the ruler anymore. Throw away the ruler. Not here, I'm saying. Yeah. Suddenly there is power to you. One flip of an idea that the markings on the ruler are equivalent to waves immediately throw so many ideas. All I have to do is same co-prime I have to use over here. The mathematics that helped Vernier invent Vernier calipers today can measure to an angstrom level. Can you imagine? So you have nanometers, etc., being measured so routinely by laser interferometer. So you combine lasers, you combine the frequency, you got all kinds of measurements that are possible today, which were not existent when Vernier discovered, oh, okay, I can make measurement accurately. Invention. This is very important for you. How did this happen? How did this happen? Laser interferometer. What could be that trait of that person which brought this in? Okay, so I'm going to introduce to you one more trait that is important for the inventor. Two traits we already saw, two habits that we also. Third habit is what I'm going to talk about. That's a very, very important habit. Becoming stronger in that habit will make you definitely an inventor. Okay, but before that, one small problem. I have a single block of ice on one side, 8 cubic blocks of ice. Shall I skip it because 10:30? I want activities. Yeah, I'll skip this. But basically, what I wanted to tell you is, I told in the introduction sometime about Wang Chuk, who used the simple idea of surface area to volume ratio as the heat dissipation in order to come up with the ice to pass. I'm going to skip this, but I want you to watch this one because this is a very important one.
Please close your eyes
Close
and
your eyes.
open your hands. Now imagine what you could place in your hands. An apple, maybe your wallet. Now open your eyes. What about a life? What you see here is a premature baby. He looks like he's resting peacefully, but in fact he's struggling to stay alive because he can't regulate his own body temperature. This baby is so tiny he doesn't have enough fat on his body to stay warm. Sadly, 20 million babies like this are born every year around the world. 4 million of these babies die annually. But the bigger problem is that the ones who do survive grow up with severe long-term health problems. The reason is because in the first month of a baby's life, its only job is to grow. If it's battling hypothermia, its organs can't develop normally, resulting in a range of health problems from diabetes to heart disease to low IQ. Imagine, many of these problems could be prevented if these babies were just kept warm. That is the primary function of an incubator. But traditional incubators require electricity and cost up to $20,000, so you're not going to find them in rural areas of developing countries. As a result, parents resort to local solutions like tying hot water bottles around their babies' bodies or placing them under light bulbs like the ones you see here, methods that are both ineffective and unsafe. I've seen this firsthand over and over again. On one of my first trips to India, I met this young woman, Savita, who had just given birth to a tiny premature baby, Ronnie. She took her baby to the nearest village clinic, and the doctor advised her to take Ronnie to a city hospital so she could be placed in an incubator. But that hospital was over 4 hours away, and Savita didn't have the means to get there. So her baby died. Inspired by this story and dozens of other similar stories like this, my team and I realized what was needed was a local solution, something that could work without electricity, that was simple enough for a mother or a midwife to use, given that the majority...
What do you think she would have done? In fact, two of them, this is Chen. The other person was an alumnus, is an alumnus of this institute. They both did this together when they were students in Stanford. What do you think they would have done?
Please close your eyes. Something that could work without electricity, that was simple enough for a mother or a midwife to use, given that the majority of births still take place in the home. We needed something that was portable, something that could be sterilized and reused across multiple babies, and something ultra low cost compared to the $20,000 that an incubator in the US costs. So this is what we came up with. What you see here looks nothing like an incubator. It looks like a small sleeping bag for a baby. You can open it up completely. It's waterproof. There's no seams inside, so you can sterilize it very easily. But the magic is in this pouch of wax. This is a phase change material. It's a wax-like substance with a melting point of human body temperature, 37 degrees Celsius. You can melt this simply using hot water, and then when it melts, it's able to maintain one constant temperature for 4 to 6 hours at a time, after which you simply reheat the pouch. So you then place it into this little pocket back here, and it creates a warm microenvironment for the baby. Looks simple, but we've reiterated this dozens of times by going into the field to talk to doctors, moms, and clinicians to ensure that this really meets the needs of the local communities. We plan to launch this product in India in 2010, and the target price point will be $25, less than 0.1% of the cost of a traditional incubator. Over the next 5 years, we hope to save the lives of almost 1 million babies. But the longer-term social impact is a reduction in population growth. This seems counterintuitive, but it turns out that as infant mortality is reduced, population sizes also decrease because parents don't need to anticipate that their babies are going to die. We hope that the Embrace Infant Warmer and other simple innovations like this represent a new trend for the future of technology. Simple, localized, affordable solutions that have the potential to make huge social impact. In designing this, we followed a few basic principles. We really try to understand the end user, in this case, people like Savita. We try to understand the root of the problem rather than being biased by what already exists. And then we thought of the most simple solution we could to address this problem. In doing this, I believe we can truly bring technology to the masses, and we can save millions of lives through the simple warmth of an embrace.
So they started in 2008. It's about 15 years now. They were able to save about 200,000 so far. Wonderful, no? What did they connect to? What concept did they connect to? You know the name of that? Latent heat. It is latent heat. Water turns into ice. Water turns into steam. When it is transforming from water to steam, exactly, the temperature does not change, right? So they tried to use that. Simple hot water or stove is enough to heat it up, correct? So you did not need anything else. Somebody said sun, you keep it in sun. That's another way to do it. But it was now possible for anybody who did not even have electricity in their home to be able to save a premature baby. Why? Because they could connect what they learned in the class to a problem out there in the society. So you really want to be people who can make a change to make a better world. All you need to do is pay attention in the class. What, Ananya? Pay attention. You're not well? You're okay. Pay attention in the class, understand the concepts well, then it's possible for me to connect, right? All it takes is a bunch of concepts that I can internalize for myself. That's what is important. She used just this principle, which we all know. And therefore, folks, the third habit is getting immersed. When you immerse in the problem, whatever concepts that you got will click at a particular time, because you'll just run over all those concepts that you learned and you'll become an inventor. Okay, I promise. Okay. Quickly, 2 more minutes will take. I'm going to just throw up a phrase and you will tell me. Hot air is less dense and rises up. Hot air balloon, convection currents, fantastic fan, right? So note what is happening to you. You are now connecting. What is existing? Perhaps what could exist later, right? Quickly, black surface absorbs radiation. Huh? Yeah, actually silver a type of paint is used in the terraces. Perhaps if you go up here, you will see that. Here, of course, we have put solar panels all through. Okay? Yeah, exactly. This is an aluminum tube. This is some metallic object. I don't know if you've seen. Can you catch it? You can probably hold it so that you're taller. I'll hold this. You can leave this one. Again. Just watch. Observe. Yeah, too many times. Here. Oh my God, it's not coming. Oh, okay. Where is it? Oh, here. Oh God, this is faster. Why is this slower? My God, it takes time. It's a magnet. This is a magnet and it is passing through this aluminum tube, moving. it's creating an electric field EMF, and what is happening to the EMF? Okay, it interacts. Okay, as I do this over and over and over, what will happen to this? Not only that, when electricity passes from one point to another point through a wire, it gets heated up. So it's actually eddy currents that form, and as you do this over and over, it gets heated up. Actually, the kinetic energy of this is sort of resisted when these eddy currents form and sort of apply a resistance to this motion. All right, where shall I apply this? Where shall I apply this? So, in fact, if I take this magnet and I have an aluminum plate, I bring it down, very difficult to hit that plate. Very difficult to hit that plate. In fact, Dharmi has, oh my god, yeah, Dharmi has a very, oh sorry, I shouldn't have brought all this together. Yeah, very heavy magnet. So, if I bring it closer to this, very difficult if it is a plate to hit the plate. Application, where shall I apply? Bullet trains, magnetic suspension. It's actually not suspension though.
Levitation.
Not levitation. It's only when it is falling. So let's say I drop this magnet, or I drop the plate and magnet is below. What will happen? You may think, oh, okay, it will go and hit. No, it will go and softly land on it.
Safety for
Yeah, any suspension or for safety's sake in a lift, etc., this will be very useful, right? Simulating gravity is one possibility. One possibility. So, I want you to keep thinking, okay? That's what is more important. I'll move on. Where do you start? Moms will not like it. Start from kitchen, because that has enough number of materials that you can try it out. Which material in kitchen is it? Anything, even chapati dough is fine. But Earth's magnetism is not that. But the Earth as a magnet is not that powerful, and therefore it may not be useful that way. Perhaps if it is a directed landing, what you're talking about could be very useful. Yeah, correct. Yeah, right. So instead of using spending fuel, you can use that. Very good. For
example,
okay.
they have safety nets.
So in general, for safety, right, for objects that have to land softly, you can use this. There are two options. I have only 10 minutes. There's a lot of materials that we have to show, right? So what are the options we have? Who should we ask? This is just to give you an idea. lot of them which are very cool. This is nice. This is nice. And of course, I've deleted the other one because it pertains to you, so I deleted that. It's a small child having a laptop on his lap and doing work. I'm talking about 3-year-old. Let me end this with a story. So a visitor visits a temple, but the temple is still under construction. So usually when the visitor goes, what do? They stop at a worker and ask, "Oh, what are you doing?" "Sir, I am putting one brick after the other. That's what I am doing." And then he goes to another mason, asks the same question. "Well, I am building a wall. I am laying the bricks and building a wall." And then he goes to another person and asks, "What are you doing?" The person says, "I am building a temple." What do you understand from this? What do you understand from this? Huh? Big picture. So think of big picture. When you are doing something, it is connected to that big picture. If that is there in us, it's easy for us to understand why we do what we do. Yeah? And therefore, you will develop competence by yourself. And who will be responsible for that? My mom, sir, my dad, sir. No, it is you. So take control of your learning, not somebody else. "Oh, it is not in the syllabus, madam." Yeah. Right? Doesn't matter, because I want to learn, right? So do that. Then what Venkatraman Ramakrishnan states will come true. Do what interests you. Many of us could not do it, but it is possible for you today. Do what interests you. When I told my son, "You can join this institute, it's a great institute," and all those, I gave a big marketing thing. He said, the next day he came back and said, "No, Dad, I love science." And he said, "I will go join a science institute." He went and joined a science institute. He is happy doing it. So, what interests you, find out what interests you and move towards that. Okay? You will not repent for it later. This is my humble request. Sky is no more the limit. You all know it now. Thank you.